This is the first of 3 videos showing different approximations which are used in hypothesis tests. In the first one, we're going to show what happens with a normal approximation to a binomial distribution. Firstly, let's remember that a normal distribution, n mu sigma squared, is a good approximation to the binomial distribution, BNP, with mu equal to np, sigma squared equal to np1 minus p, when n is large and p is near a half. Roughly, that means between 0.2 and 0.8. It does depend on how big n is. Well, with this example, I'm going to take a treatment of patients under a drug. With a current drug treatment, 20% of patients are cured. A new drug is given to a random sample of 100 patients, of whom 26 are cured. Does this indicate, at the 5% level of significance, that the new treatment is better? Use a suitable approximation. Well, we need a hypothesis. Null hypothesis is the no change hypothesis. P is equal to 0.2. Alternative hypothesis, we're asking whether the new drug is better, so we're asking whether P has increased. So we have a one-tail test, and we're using a 5% significance level. X is the number cured in a sample of 100 patients. Now, we cannot use our cumulative binomial tables for this, but we can use an approximation. 0.2 is just on the edge of P is near a half. On the other hand, n is 100, which is really quite large. So in this case, we have that x is actually binomial 100, 0.2. We want the expected mean, mu, which is np, which is 100 times 0.2, which is 20. And sigma squared is np 1 minus p, which is 100 times 0.2 times 0.8, which is 16. N large, p near 0.5, so we use a normal approximation. And here I do like to change the letters. Very good reason for it in this instance. Y, twiddle, normal, mean 20, and variance 16. And here I've got a graph to show the approximation that we're using. The red rectangles are the binomial distribution at 20.2, and you can see the black normal distribution curve is the distribution curve normal, I should have an n there, 20, 4 squared. Okay, now we are in a position to go ahead and test. The test statistic x is 26. So we are looking for the probability that x is greater than or equal to, I keep emphasizing the equals, 26. This is why I like a different letter. It's approximately equal to, it's an approximation, the probability that y is greater than, well, if we want to include the rectangle 26, we've got to start under the normal curve at 25.5. So the value that I'm using for y is different to the value that I'm using for x, which is why it's a good thing to have different letters. Now we can just plug in our normal distribution theory. That's the probability that z is greater than 25.5 minus the mean, which is 20 over 4, which is, let's move up a little bit, the probability that z is greater than 1.375, which is 1 minus the probability that, because this is how we use our table, z is less than 1.375, and that is equal to 0.0838, which is 8.38%. That is greater than our significance level, and therefore not significant. When we're looking in the tables, we must use z equals 1.38. We don't have 1.375 in the tables. Having decided that the result is not significant, we are going to accept H0, and we're going to conclude that there is evidence that the proportion of patients cured is not greater than 0.2, or that the new drug is not better than the old drug.